Hello everyone. So in this video clip, I'm going to summarize what we've covered in this chapter on electrostatics. So first of all, objects can have a property called electric charge, symbolized by Q, such that they exert a force on another object that also has an electrical charge. If their charges are Q1 and Q2, the force between them is given by K Q1 Q2 over R squared. And this is Coulomb's law. So in physics, you have three main categories of equations. You have laws, you have definitions, and you have formulas. So law is a statement of fact. It's an observed pattern of behavior. So that's just the way nature is. And in this Coulomb's law, this constant K is 9 times 10 to the 9 Newton meter squared per Coulomb squared. Then this force equation can be broken down into a field created by the first charge, which is K Q1 over R squared, and the effect of that field on the second charge, E, that electric field times the second charge. So this is similar to the analogy of the fan blowing the piece of paper. Instead of talking about the fan blowing the piece of paper, you can think of the fan as creating a wind. And then the wind is what's affecting the piece of paper. So the electric field, that's like the wind. It's a vector field. So here the equation E equals K Q1 over R squared. This is the formula that gives you the electric field due to a single point charge Q1. This can be derived from Coulomb's law. So this is an example of a formula. On the other hand, F equals EQ2. This gives you the effect of an electric field on a second charge and the force that it creates. This is a definition. This defines the whole concept of the electric field. Then a note about this equation here, Coulomb's law. This expression, the force K Q1 Q2 over R squared, it gives you just the magnitude only. The thing that comes out of here is always positive. The directions are determined separately. The line of the force is along the line that joins the two charges together. And then the force is repulsive if the signs are the same, is attractive if the signs are opposite. Another note about Coulomb's law. It has an inverse square law behavior. The force is proportional to 1 over R squared. So this inverse square law, the proportionality to 1 over R squared, it's ubiquitous. Sound intensity, light intensity, gravitational field, spray painting a wall. In all of these situations, as you double the distance, the intensity becomes 1/4. And that's simply because as you increase the distance, the stuff that's being projected outward, whether it's an electric field or spray paint or whatever, that's spreading over a bigger area. And that area is proportional to R squared. So the field or other entity like paint, it gets diluted as 1 over R squared. In addition to Coulomb's law, you have the law of superposition of forces and electric field. So this tells you that if you have 3, 4, 5 charges exerting forces on each other, you can find the total force on any one charge by vectorially adding all the forces from all the other charges. Same for calculation of electric field. You can vectorially add the different electric field sources to give you the overall electric field at any point. So this too is a law. It's an observed pattern of behavior. So this is used in combination with Coulomb's law to find electric forces and fields for complex geometries. Next, you have the business of the electric field lines. So if you have a positive charge, if you place a test charge over here, a second Q, it's going to feel a force. If you put this a test charge at different places and you complete a locus of all the points of that force, these are the electric field lines. So it tells you at any point in space, if you put a charge there, what will be the direction of the force. Notice over here that the lines are more concentrated closer to the charge. They are farther apart as you go farther away. So this dilution of the electric field lines is an indication of how strong the electric field and therefore how strong the force is. Another thing to note is in the case of a positive charge, the electric field is pointing outwards, and so are the lines. In a negative charge, if you were to place a positive test charge, it's going to get attracted, so the lines of force are inward, so these electric field lines are pointing inwards. But once again, where the field is stronger, you have a greater concentration of these lines. Now, a consequence of that is that if you have a sharp point, like a needle or something like that, then in this end region here, that represents a circle of a very small, tight curvature. So as a result, the field lines are more crowded over there. So for a pointed conductor like this, the electric field is strongest at the sharp point. This is why lightning conductors on top of tall building, they end in a sharp point. So this way you have a higher buildup of electric field, and lightning is more likely to strike that point and then run down the conductor to ground rather than cause damage to the building itself. Next, you have this concept of electric flux. So if you have an area that's facing this electric field, or any field, a vector field for that matter, then a certain amount of field lines are caught. So how many are caught? This is kind of the spirit of this physical quantity, electric flux. More quantitatively, if these lines are closer together, that indicates a stronger electric field. So the amount of flux that you catch by a surface, it depends on E, the electric field. It also depends on area. If you have a bigger fishing net over here, you'll catch more fish. So if you have a bigger area that's facing the electric field, that's going to give you more flux. So you have E and A. And the cosine theta, that just tells you want to make sure the surface is facing that field to catch the most number of line. So that's governed by cosine theta here. E dot A is kind of an abbreviation for EA cosine theta. And this too is an example of a definition. So E and A are already defined. We are combining them to define a new physical quantity, and that's the electric flux. This now brings us to Gauss's law. This tells you that if you have a closed surface completely enclosing the charge, then it catches all of those field lines. So all of that electric field is caught. And in that case, you can relate the total flux through this closed surface, like a sphere, to the charge enclosed. And that connection is that phi E, the electric flux, is equal to 4 pi k times Q, where Q is the enclosed charge. Sometimes this is written more succinctly as Q over epsilon 0. Here epsilon 0 is another constant, is simply equal to 1 over 4 pi k. And this again is a law because it's an observed pattern of behavior. This can be derived from Coulomb's law. However, you can view the Gauss's law as the fundamental law and derive Coulomb's law from it. So it's kind of parallel to the Coulomb's law. Next, we have the concept of the dipole moment. So if you have two charges, a negative and a positive, separated by a certain distance, then that constitutes an electric dipole. The magnitude of the electric dipole, it's called the dipole moment, P, little p, and that's equal to Q times D. So the more the charge that's separated, the bigger the dipole moment. The greater the distance d over which it's separated, the bigger the dipole moment. So the combination of QD gives you P, the dipole moment. When a dipole is placed in an electric field, there is no net force on it because you have a minus and plus or opposite charges. So the total force, the net force, is equal to 0. However, there's a torque on it because the positive is pushed in one way, the negative is pulled in another way. This causes a rotation. That leads to a torque. And the value of the torque, the vector equation, is torque symbolized by this little tau. That's equal to P cross E. So this expands to give you the magnitude of the torque. That's equal to PE sine theta. So P is the dipole moment, this business here, the Q over Q times D. E is the electric field. The electric field is what causes the forces and hence the torque. And then sine theta. If there's a tendency for the dipole to align parallel to the electric field. So if it's not parallel, the more off that angle is, the stronger the torque to causing it to get aligned. So hence the sine theta over here. So because of this tendency to align a dipole, if you forcefully flipped it in the opposite direction, there'll be a torque which is trying to bring it back into alignment. So the total energy to flip it all the way from 180 degrees back to zero, that flip energy is 2pe. So P is the dipole moment, E is the electric field, double that. That's the energy required to flip the dipole. And in a microwave oven, the food has dipoles, water molecules have dipoles, for example. So you have an electric field that's flipping all the time, back and forth. It's an oscillating electric field. And this causes the dipole to flip from one direction to the other over and over again. And frictional processes are involved. That leads to heat. This U-flip energy, that ends up warming up the food, and that's how a microwave oven works. Then coming to various materials that may or may not display electrical properties, you have a broad division into conductors versus insulators. So some materials like metals, the electrons are free to move, so as a result they can carry an electric current, they can transfer charge. On the other hand, materials like plastics and glass and so on, these are insulators, so they do have electrons, but those electrons are not mobile. So if the charge is not mobile, this will not conduct electricity. This constitutes an insulator. One of the properties of conductors is that there is no static electric field inside a conductor. So if you apply an electric field or if you add charges to a conductor, they move around until there's no electric field in the body of the conductor. And the unbalanced charges, they sit on the outside of the conductor. And this concludes the summary of the chapter on electrostatics.